Well, hello friends. Today we're going to work on scheduling in Serenity OS, and we're going to make it a bit more sophisticated because we've been kind of stuck with kind of a pretty naive scheduling algorithm for quite some time. A while ago I made it so that it's separated by priorities, so we have effectively three priorities right now. We have low priority, normal priority, and high priority. And you can see these little arrows here that they indicate which priority a certain thread has. But there's not much more to it than that. And it makes it kind of difficult to do more sophisticated things like giving a slight priority boost to, for instance, a window that's in the foreground at the moment or something like that. Because the only option you have is to bump it from like normal to high. So it would be cool if we could have a much finer system for priorities, and then also right now, if there is a high priority process or high priority thread that wants to run, the scheduler will always schedule the highest priority thing. So it's very possible to get starvation to happen if you just have something high priority that wants to run all the time. None of the low priority stuff is ever going to run. So today I'd like to do something about that, and I don't know much about scheduling algorithms. I haven't studied them or anything like that, and I haven't really read about it, but I've used some APIs in my life, so I know sort of what tends to exist. So my thinking is that we will give each thread like a priority number between, say, 1 and 100, and then there will be like a base priority number. So say that what we today call high priority would have like a base priority number of, I don't know, 50, right? And then say normal would be 30 and low would be 10 or something like that. And then whenever we schedule a thread, we reset that thread priority to its base priority number, and for every thread that we don't schedule, we increment their priority by 1. And so next time the scheduler runs, those threads will all have moved up, and we always choose the one with the highest number. And by doing it this way, we basically make sure that even the lower priority threads, they're eventually going to bubble up and have a high enough priority number that they will preempt a high priority thread because it has been scheduled and it was reset, and it was finally reset to its base, which would be below what the lower priority thread has now been incremented to. So that's sort of my thinking for making the scheduler actually eventually give a chance for these low priority threads to run, so that we never starve anyone completely. And I don't know, maybe this is like a really naive solution or something, I don't know, but I figured we would try to implement that today and see how that works out and see how we can visualize it in the system monitor. So let's take a look at the thread priorities the way they are implemented right now. So each thread has this priority thing right here, and it's just a member of the thread object. So I'm thinking we'll just straight up change this to be a, I mean, why don't we just call it a U32 for now, priority, and maybe we will priority normal. We'll have to have something for this, but I don't know exactly what it's going to be. Where are the thread priorities? Right here. So maybe we will, we can do them like this. So what was I saying? 30, 50, and 10. And then, yeah, like I was saying, whenever you don't get scheduled, we're just going to increment this. And I think we'll make an exception for the idle thread or the kernel thread. and just never increment that one, because we never want the idle thread to preempt anything. That's the whole point. Like, it should only be scheduled if there's nothing else to do. So this here is just it's only used by the kernel's idle thread. So I think we can stop thinking about that. So okay, so now these guys right here, maybe we'll say that they're unsigned just because. Okay, and then, or wait, what is the POSIX API for this anyway? It's like what the heck is it called? Sched set param? Yeah. And the param has sched priority, which is an int. I think we can't have negative numbers, so we're just going to go with the U32 for this. I think that's okay. And then we will just bounce check that it's not negative in the API layer, or in the API. Let's just call API. All right, and then down here, this is where we were. So previously we've been having like the separate thread queues or thread lists divided by priority, but that's not going to change. So instead we are just going to stop caring about that, and we're going to segregate. We're only going to segregate by whether a thread is runnable or not runnable. And then, I mean, in the future, we would probably want to segregate, have a separate run queue per CPU or per core, something like that. But right now, since we're not doing multiprocessing, then we can just worry about a single queue of threads. And guess if it's runnable, then we will give you the runnable thread list. So this is just a helper for giving you the which thread list to use for a specific thread state. And the runnable states are running and runnable. So okay, so for each runnable, this function, just stop caring about the threads. Is that how we do it? No, it's G scheduler data, something like that. And okay, so now we only have one big bucket of threads, and oh wait, how did I do that? Oops, oopsie doopsie. So then, when we get the thread list, we no longer have to pass in the priority, because we don't segregate based on priority anymore, only by state. Okay, and then previously we've had this for each runnable with priority, which is how we iterate the threads that we're interested in. And then another thing that we've been doing is we've been choosing the time slice that each process gets to run based on its priority. And right now I'm thinking maybe we'll just not do that. I think maybe we won't do that, but the difference, the thing that we'll do differently is that for the idle thread, we never want it to run more than one time slice without waking up and checking if there's something new to do. Although in the idle loop, we kind of already check on that. Well, we'll wake up, because we get an IRQ, the idle loop will wake up, we'll discover, hey, I should stop idling. And so it will yield. But even so, we have to make sure that we don't allocate more than one time slice for the idle thread. Otherwise, we will, even though we get an IRQ from some hardware, we would still idle for like 5 other more milliseconds or whatever before dealing with the IRQ, which would be stupid and introduce latency. So we want to avoid that. Anyway, so I think we don't need this for each runnable with priority, so we can get rid of that. And then time slice 4 is used in 2 places. Time slice 4. Instead, we can maybe just pass it a thread, and then we'll just look if that thread is the idle thread. We'll say if thread is the kernel thread, return 1 millisecond. Otherwise, I don't know, how long should our default time slice be? I'm thinking maybe 10 milliseconds. That's quite a long time if you run the whole slice. But what were we doing before? Doing 15 for normal? 10 seems like a decent enough time. Like, you can do a lot in 10 milliseconds if you're a CPU. So most of the time, threads don't end up using the whole time slice anyway. It's only the really, really busy programs that do, like if you're running Quake or something like that. We'll see. We may have to backtrack on this one. I just feel like right now that it might be interesting to not have separate time slice sizes per thread priority, but instead just have a one size fits all. But I'm sure that I'm probably wrong about that. We'll see. So now we got to look at when we are gonna choose which one to run and which ones not to run, and then increment that priority thing like I was talking about. And that makes me realize that we need more than just one number here. We're gonna need a base priority, and then I think we should also have a effective priority. Something like that, or maybe we can even have this be a maybe like extra priority or something like that. And we'll start that out at 0, and we'll increment it by 1, and then the priority will be, the effective priority is base plus extra. Okay, so let's do that. And maybe we'll call this priority, actually. That was not a terrible name. And we'll have effective priority, like that. Okay. And maybe we should make sure that we expose this right away in procfs. So in the thread info, next to priority, we will also show the effective priority. And let's just make sure we pick that up in the processed statistics. And these can be numbers now. So just gotta populate these things to U32. Okay, and finally in the UI in the system monitor, let's add a column actually. So we call it the effective priority. That's the PR, and we'll call it the EPR maybe. Okay, this is going to be very interesting because scheduling has really been holding back a lot of interesting things that I would like to do with priority boosting and stuff like that. And just getting this building block in place is going to be very helpful for unlocking new opportunities. And we're definitely not going to do like the perfect data structure today. We're just going to like get the mechanism into place, and we can worry more about data structures later. That's something that I really love about C++, by the way. I know I've mentioned this in the commute talk sometimes, but the fact that in C++ it's quite easy to prototype something, get it into a good runnable state, and still not have like the perfect data structure chosen from the start, and it's still quite easy to come back later and factor in a better data structure, because you can, the language just lets you abstract things in such a way that the data structure can be swapped in and out, whereas in some other languages it's harder because you become more tied to the particular choice of data structure. I think we'll just do this because these strings now go away, and the effective like that. Oh shit, we got so much this information has so much duplication going on here, but it's okay. Priority. Okay. And we've been using these icons for the priorities, but we're going to change that and not use the icons anymore because they're not going to be, high fidelity enough. It's going to be much more information here, so I don't want to hide behind icons. It's okay though. I have to say I really love putting more information into the system monitor. It's so much fun to see. Like, it's such a great window into what the kernel is doing. The more you know about the kernel, like the more value you get out of system monitor. It's really making me appreciate just how interesting commands like ps and top and stuff like that must be to people who know more about the kernels on other systems. Anyways. Oh wait, I've already done this part. Alright, so that's good. Now let's go back to the scheduler. And okay, so let's let's just enable all of the debugging options so that we break the build and have to fix all this stuff. So we no longer need to iterate over the different priorities because they don't exist in that old sense, or the at least not the queues. We'll just have runnables. We have runnables and non-runnables, right? That's what we have. So we'll have a scheduler for each runnable, like this. Okay, and then here, we've been iterating over the priority queues. So we're going to change this now, and we're going to take the runnable queue, and we're going to sort it by, because it's not sorted, so we're going to have to sort it. And here's an example of why I was saying this thing about the data structures. It's like we're not going to build a new data structure for this, even though you could imagine a much more efficient, like automatically sorting one, but we'll just sort on the fly. So we'll make a vector of threads with a inline capacity of 128 to avoid heap allocation unless we have very many threads. And we'll say sorted runnables. Okay, and then we will, for each runnable, we'll just put them in the in this guy here. So sorted runnables, append thread. That's pretty simple. And then we will quick sort. quick sort the sorted runnables. Oops. Sorted by effective priority. Effective priority. Okay, and then we're gonna start with, what are we gonna do? We're gonna pick the highest priority one. I guess we can dump out what we have here. So, or so the criteria here for what's runnable is that it has to be runnable or running, which actually these should always be true if something is in the runnable list. So we shouldn't even need to check these. It's really weird. Why do we even have that condition? A thread should not be in the runnable queue if it's not one of these. So we'll make that into an assertion, I think. So assert. But this is important. So if the process of the thread is being inspected, then that's a temporary state where you're left in the runnable queue, but something in the kernel is currently inspecting this process, so we don't schedule it. It would probably be a good thing to refactor things so that inspected processes be put in the non-runnable queue. But right now, they stay in the runnable queue, so we have to deal with that state here. And it's used, for instance, by the proc file system to make sure that a process doesn't get scheduled while we're looking into its internals. This is what we care about, the runnable threads, runnable list, but actually we don't even care about this list because we care about our own sorted list here. So we're just going to start at the, let's see, thread in sorted runnables. So the highest priority should be first, and actually, if there are no sorted runnables, yeah, if it's empty, then we'll just come down here and schedule the idle thread or the kernel thread. But what are we doing here? If the thread, wait, how are we going to do this? So we're going to store a variable here because we're going to have to visit all the threads anyway because we want to increment their effective priorities or their extra priorities, right? So thread to schedule is the kernel by default, and thread to schedule. So if we don't find one, we'll fall back to the kernel, right? And if someone is being inspected, then we'll just skip over him, I think. And here we can put this down here. We'll say thread to schedule. We'll put the thread's own name. I'll just fix this up real quick. Okay. And then we can skip over this part. Because what we want to do next is we want to we don't care about the order of this list anymore. We just care about the priority numbers. So we don't have to rejig this queue, but instead we want to say thread to schedule is thread to schedule. Or say thread m extra extra priority 0. And we can assert that it's in a good state. And is this everything that we need to do? I don't care about the runnable list. Okay, I feel like we're definitely missing stuff here, so we're gonna have to clean up some build failures. Seems like maybe we're not running with the kernel defined. Okay, so we have some red down here. Right, no thread priority enum anymore. Oh, it was right there. Thread state. Oh, that's just Clang. But this guy we can remove because there's no way to stringify thread priorities anymore, which is okay. And probably in process CPP we have something to fix. And we got the thread priorities, and same in procfs. These don't become strings anymore. Because previously they would just be the string like low, medium, high, or low, normal, high. But now it's not like that anymore. So here instead we'll say if sched priority is less than 0 or sched priority is above 99 maybe, I don't know, U32. We'll let you specify in this range. I think sched set param. Oops. What is the max? Get priority max. Don't like it, show. 1 to 99 is the Linux range. I guess we can go with that. Okay. So create thread, right? Priorities. Well, let's add defines for these. Maybe we'll let you do this. Requested thread priority. Wait, oh, it was right here. All right. I think maybe we'll let you make high priority threads, even if you're not super user. Because we can still do that. And then maybe we'll just throttle you somewhere else. But I think we need to allow user space to create whatever priority he wants, basically. All right, so what did we mess up now? Scheduler. Well, there's no toString for thread priorities, that's for sure. I guess that was right here, so that becomes a U. And then we got some red right here. Just set that to the minimum priority, the kernel thread. Effective. So I guess here, when we're quick sorting, I gotta use these because we're iterating over pointers, not values. Then I'm forgetting to return an iteration decision on 359. All right. Oh, wait, hold on, not break, continue. An init thread priority. Okay, let's do a full build here because I changed a bunch of user space things, but not that many, just a few. So it'll be fast because of Zcash. And also, I have to get better about not using makeall all the time because incremental rebuild is supposed to work, and you just keep typing makeall out of habit. Sorry, Joshua. Okay, so, oh, top, we forgot about top. Top command. Now, has to, oh, we can just skip that part, but we'll definitely have to change the priority display. Blindness, here we are, U32. Is this actually shown anywhere? Yes, it is. So priority was shown here. I think we'll change it to O2U, or to a 2U. Okay, let's do incremental build. It's pretty cool. All right, so what's happening here? We're looking at our non-runnables and our runnables. So system server is runnable, but in every single case, we always switch to sync D, it seems like. Why is that? It's because we never increment their effective or their extra priorities. So of course, we're just going to pick the same one every time. Where is it? Pick next. Pick next thread to run. So for everyone who's not being chosen, inspected we'll just skip over. Oh shit, no, we're always, this was a mistake. Okay, so the first one that we encounter, that's going to be the one that we schedule. So we'll start this out with null putter, and then if no thread to schedule, then we'll schedule this one. Then else, for everyone else, we'll say thread extra priority plus plus. And if no thread to schedule, thread to schedule is G kernel. Oopsie doopsie. Okay, what did we do wrong now? At this address right here, we done did a null deref. And why did we do a null deref? I guess because here we don't have a thread to schedule until we've done that. What a silly mistake. Okay. So now we have lots of runnable threads happening. All of these threads are queued. Only audio server is running at the moment. I don't know if we're actually making progress towards running or not. Taskbar is running. Are you actually gonna change resolution at some point? Not too much happening here. So who do we want to run? We want Windows Server to run, but Windows Server is not up. Okay, so we're gonna need to dump out the effective priorities and stuff. Runnable, debug. I wanna see what's happening with these things. So the runnables. Let's show the priorities here. So 2U and 2U. Let me say 3U. This will be the effective priority, and this will be the base priority. For each runnable, show the process address. That doesn't seem useful at all. So, okay, we'll just do it this way instead. I don't know why we've been showing the process address. It doesn't tell us anything. Okay. So there will be thread dot effective priority and thread priority. And we should also show the thread name, not the process name. Okay. This is leftovers from when there used to be no threads, only processes. And then, of course, the scheduler was always thinking in terms of processes. And some of these printfs are still from that time. So let's see what we have now. 3030. So what is going on here? This one is a higher priority task. And we can see syncd is going up one step, another step. It's kind of cool. So we got this guy right here running at very high priority, and he doesn't get to, this guy doesn't get to run until this guy has run for 20 time slices. So this is basically what I wanted to achieve, right? But what do we see here? Oh, the base time slice of these guys. I guess we're setting them from user space. Where are we doing that? System server service priority, right? And oh, here they are. Okay, so idle, we shouldn't support idle because it's only for the idle thread. So 30 and 50, just to match what we had in the kernel. Should probably expose those in some kind of define or something. But okay, so now we are running a lot of stuff. It's very, very spammy. So we got a TTY server going. and it gets picked because it's the highest number. Very interesting, actually. But I wonder if this works in practice. So we're gonna have to turn off all the debugging because it's just... Oh, sneeze. Jeez. Let's turn off all this debugging because I feel like it's preventing us from getting anywhere. We're progressing the boot. Yeah, there we go. Okay, so too much debug means you never get to Windows Server. So, what do we see here now? We just see everyone's priority and their effective priority, but they're both the same number, so that seems like it's not right. Where are we showing it? This is the sort row, effective priority. I bet you that we're just not setting it correctly somewhere. Is thread effective priority? Okay. All right. And then procfs, the effective priority, which is the priority plus extra priority. I really feel like we should sometimes see someone. Oh, we see this guy right here. He has a different effective priority. It's 32 perpetually. Oh, I guess because he's blocked. Oh, right. Everyone is blocked. Then what if we introduce some Quake into the mix? Oh, jeez, that stutter. Quake is running with a very low priority number. Right, of course, that's going to cause a massive stutter. So is somebody doing set param somewhere other than Quake? Why does Quake run with a low priority? I wonder if Quake is doing something. Set param. Maybe it's SDL doing it. No? Who's doing this? Who's setting the priority? Damn it. What happens if we just run some random port that we have? What about... Let's get that neon cat port. I haven't had that for a while. Oh, forgot to sync. Come on, neon cat. Shoutouts to K Lang from neon cat. All right, so neon cat runs at a comfortable 30 priority, which is reasonable. I think maybe when maybe the effective priority is not super important to show, but I guess I find it kind of interesting. And it is a bit funny that shell manages to not get scheduled twice before blocking, and then when you're blocked, then we don't reset your priority. Because you could imagine doing some kind of interesting things like giving someone a boost to their priority if we unblock them because some IO finally finishes and things like that. There's a lot of interesting things you can do when you have more dynamic priorities like this. But now I'm really wondering, why was Quake doing that? So, I mean, I guess it's doing a sched set param for some reason. Or wait, was that a secondary thread? Oh shit, I bet it was a secondary thread and it's statically linked with the old pthread code. Yeah, it's this thread right here, because look, the main thread of Quake boots up in a normal thread priority, but the secondary one, it's statically linked with our libp thread. So we're just gonna have to rebuild the port real quick. Maybe this is super quick actually. Alright, I got Quake here, and no, bad prio. Okay. Have to make sure we install libp thread if we change something, otherwise the port won't pick it up. I'm starting to look forward more and more to dynamic linking. Now Andrew started working on it, so it's very exciting stuff. See how it's going for him. But right now, let's just continue whatever it was I was doing. Totally spaced out there for a moment. Damn it, no, why is it still low? Do I have to rebuild SDL? Is that it? I mean, fine, be that way. I'll rebuild SDL, I don't even care. Maybe I am actually stupid right now because we are setting a low priority number and I don't even realize. Yeah. So what's going on here? This must track blah blah blah. So I'll do that. Should use defines here. Create. Pthread. Did we have some default priority or something? Prio. Does this have it has a default number? Aha. Okay. So probably I didn't need to rebuild SDL or just Quake probably, but I definitely had to do some rebuilding. Sometimes it's like I try to be clever and rebuild less, and then I end up struggling because I don't rebuild the right things, and I end up spending way more time than I would have if I would just do a full, clean rebuild of the world every time. But, well, it's clearly not worth doing that every time. So let's go to Quake and just reinstall that. Okay, now please let me see some Quake with the appropriate priorities. Still not. Damn it. Oh shit, I forgot to install pthread. This is just gonna go on forever, isn't it? Come on. Come on, quick. Finally. Here we are. Okay, so now we can see that these effective priorities, we catch them a little higher quite often here. Because it's been 2 time slices each since they were scheduled. It's very, very cool. So now we could imagine doing things like you could have an API where, for instance, Windows Server would be able to tell the kernel, like, hey, this process is in the foreground, or this thread is in the foreground. Give him a little bit of a boost. I think that would be something extremely cool, because then we could let Quake right now, if you foreground it, it could have a little bit higher priority, so it would get scheduled a little more often than the CPU graph and system monitor and stuff like that, and they would have to, you know, wait a little, just that millisecond, 10 milliseconds extra sometimes. And oh, I guess we ran out of Quake demo here. Do we have the game? Yeah, we do. I wonder if it still stutters. I mean, the sound. Crank up the volume here. Cool. Not so stuttery. Oof. All right. Well, we got a lot of changes. So I guess we'll start by committing the everything, I guess. We have to commit everything at once because the priorities changed from strings to numbers. But we should do defines for these though. So where do we put this? Maybe UniSTV. So let's see, where did we do this stuff? Here, right? So thread priority min, if it's less than min or more than thread priority max. And we'll just take these and put them in UniSTV. The header where you can put everything that you don't know where to put. Okay. Maybe we should be good boys and put them in serenity.h. Next to our futex things. We have futexes now, by the way. They're not perfect, but they're pretty cool. Thread priority min. Futexes are used to implement pthread condition variables so that they can block. Oh, I need to go and implement mutexes using futexes as well, but I haven't done that yet. So, do we have 99 anywhere else? And do we have less than 1 anywhere else? Probably in a million places. No? Well, some places. I don't know. That's pretty good. Okay, so let's say kernel factor scheduler to use dynamic thread priorities. Threads now have numeric priorities with a base priority between 199 and the 1 to 99 range. Whenever whenever a runnable thread is not scheduled, its effective priority is incremented by 1. This is tracked in a separate extra priority. This number is tracked. This is tracked. Okay. When a runnable thread is scheduled, its extra priority is reset to 0, and an effective priority of a thread is m priority plus m extra priority. to 0, and the effective priority returns to base. This means that lower priority threads will always eventually get scheduled to run once the threads above them, once its extra priority, or once its effective priority becomes high enough to exceed the base priority of higher threads above it. Now, the initial low, normal, high, previous priority, low, normal, high, are now as follows. The now replaced as follows: low 10, normal 30, and high 50. In other words, it will take 20 ticks for a low priority thread to get to normal effective priority, and another 20 to reach high. This is definitely not perfect, and I've used some quite naive data structures, but I think the general mechanism will help us build this. I think the mechanism will allow us to build various new and interesting optimizations, and we can figure out better data structures later on. Okay, so pretty cool. Why don't we try that window server thing that I was talking about? So if a window is in the foreground, then we will give him a little bit of a boost. Now, how would we do that? Because we don't want to raise his base priority, and we don't want to change his extra priority. I guess we can have a boost number. Something like this. And do like that, and this number priority boost will allow you to set this using some kind of API. How do we do that? We or maybe should this be it should be per thread. Yeah, I was just thinking, should it be per process or per thread? But it should be, maybe it should be per thread. Yeah. Because then it's up to like the Quake has this secondary thread. I'm not sure what it's used for. I guess we can look at it. Oh shit, it's so loud. So what is this doing? Oh, can barely see it. Oh, it's writing to the sound card. Okay, so it's a sound thread. That's going to be blocked most of the time anyway, I guess. Or well, based on the CPU usage, it wasn't blocked most of the time, but or it was not just blocked. But anyway, I think maybe it's okay if he has a slightly lower priority than the GUI thread. And then, you know, it's up to the Quake processor if he wants to do something internally. But let's try this. Let's try to just give a slight boost to foreground windows. So we would do this in the window manager, I guess. Move to front and make active. Whenever we make a window active, I think this is where we should do it. So previously active window. Right, so if there was a previously active window, we will check if previously active window has a client, and if so, we'll say client deboost and deboost. And when we are choosing a window here, then we will do this. We'll make a boost. Or not for the previously active one, but for the new active one. Okay, and then how the heck is this going to work? I have 2 cups of tea today. Sometimes you gotta be prepared, because I figured this might take some time to implement this. Okay, so void WS client connection boost. We have a PID, we have a client PID, right? So maybe we'll do like a syscall called boost thread. We'll boost it by 5. Deboost. Set thread boost. This is definitely not perfect, and it would be good if we could have like a way to have multiple sources of boost or whatever, but we're just gonna go with a very simple API right now. So we'll add a syscall for this. Enumerate syscall set thread boost. Okay, and then in process.h, maybe right here. I guess the PID of the thread, because now threads have PIDs, just like in other POSIX systems. And I guess the amount, something like that. You could imagine having a negative boost. Not sure why you would want that, but you could imagine it. Okay, PID. Okay, and then we want to look up the, I guess we want to look up the thread by PID. So we haven't really done that before. From TID. So set thread boost. This is a little bit confusing, so we'll say that it has an int because it's a TID. But this thread has to belong to me, otherwise I'm not allowed to boost it. Or if I'm super user, I guess we can allow it. But we shouldn't allow boosting or deboosting someone else's thread. But when it comes to your own threads, it should be fine to boost and deboost as you like. But we don't have thread from TID. We have process from PID. From PID. So I think we can process from PID. Let's make a thread from TID. Static thread from TID. Int. Oh shit, how do we even find threads? Threads. How do we find all threads for each living? I guess that's one way we want. Oh, we have thread for each. Okay, okay. So, for a thread for each, we'll call this found thread instead. And return the found thread. And we forgot this, and we need to. All right. And then we were in set thread boost. So auto thread. We'll have to disable interrupts for this because we're screwing with the thread tables. If no thread, return eSearch. Thread process, or let's say if thread state. Wait, what was living even checking? Because I guess we don't want to look at dead threads in this. Living checks if the thread is dead or dying. See, I don't really care for those. So thread state is thread state dead or thread state dying. And let's just say eSearch as well. And if the process, actually we'll check that first if the process dot UID is not my UID, my effective UID, then, oh wait, hold on. If is not super user, and thread UID is not my effective UID, return what is it, perm? Oh, what's the thing that we check? Is super user eperm, right? Yeah, eperm. Okay. Then everything seems okay. So thread set priority boost amount. I guess we can check if amount is less than 0 or amount is greater than 20. I don't know, some arbitrary numbers just to keep this a little bit reined in here. Don't want to get out of hand. But since Windows Server always runs as the anon user, so the regular desktop user, so it should be fine to call him. Oh shit, we forgot to create a user space wrapper for this API. Set thread boost. I don't know. Oh, well, whatever. It's not super important right now. We just need to have some way to call this syscall. So sc set thread boost with tid and amount. Okay. Set thread boost was not declared. Well, I'll say. I guess we have to include serenity.h here. Do we need IOCUDL here? I feel like we don't. Do we need any of these things? I feel like we don't. Nice, nice. So how will this go? I find this sort of thing quite intriguing. Now obviously this is far from perfect, everything that we're building here, but I think just starting to get the feel for what's possible is very important. And there's so much more you can do with boosting mechanism. Not just like whoever's in the foreground, but for instance, you can do things like whenever you send a user event somehow to a window, then you could temporarily boost that window for a burst of time. Like, you know, if you mouse over a window and you're going to send a mouse move event to the window, you can imagine like having a mechanism where the mouse move event itself sort of carries a boost, so that for the duration of the program handling that event, it would be running with a slightly boosted priority, things like that. There's a lot of stuff like that that I'll be getting into eventually, because I find it very interesting. Okay, so now this terminal here has an effective priority, as we can see, of 35 because he's in the foreground. We switch to this guy. Now System Monitor has the effective priority 35. It's really neat. So what if we run Quake then? Now Quake runs at slightly elevated priority here, as we can see, which means that it's always competing with, for instance, System Monitor, which again now becomes prioritized when I click on it, and it becomes deboosted when we deactivate that window. So I think this is like a subtle but nice little thing. Just give that slight boost to whoever's in the foreground. I like it. Alright, so then let's... I know that things kind of fall apart when we kill the Quake process. I have to look into why that's happening. But very cool. So now File Manager has the priority. Maybe the boost should be bigger, actually. We should have a boost of 10. Because why not? 5 is quite little. 10. I mean, it's not that it's quite little, because if you think about what it really means, it means that it takes 10 more milliseconds for those below it to catch up. So it's pretty neat. Yeah, I think 10 feels like a nice even number here. Cool. And CPU graph, it always runs with 30. You know, I feel like we could probably run these at a lower priority. Maybe we'll tweak that right away, because I know that's tweaked by the system server. CPU graph, I can definitely run that at a lower priority. At least I think we can. I think it will still be able to keep up. Or obviously it should be able to keep up, because it only does something once per second. And we'll probably do all of these. But something that's interesting is that these are all, the audio applet is interactive. So normally it's doing nothing, but when you click on it, you actually kind of care. And we could do the clock low priority as well. I just want to see how the system behaves with these changes. By the way, these applets here, they keep switching order because it's just, now the order is determined by whichever one starts first, I guess. Whichever one starts first ends up on the right. So now this guy started first. We can see these applets now, they are running at quite low priority, 10, which is fine because there's nothing else competing with it anyway. But what if we run Quake down? Quake is quite heavy. But we still end up running the CPU graph every now and then. I feel like this is working quite nicely. And you can sometimes see its effective priority, like it ends up running quite high, right? Because once it wants to run, it has to actually like keep incrementing its priority until it reaches 50, because that's where it would cross over above the Windows server, which is the highest priority process. And Windows server, by the way, is the highest priority process because, or thread, because you always want to be able to interact with the Windows server. It'd be very frustrating to use the system if we didn't run Windows Server at a high priority. That's something that was a little bit crappy just recently, and now it's starting to feel very reasonable to interact with the system, even though it's under extreme load. It's still very much interactive, so that's really neat. And the CPU graph is presumably updating, although I can't really tell. Now we crashed. Fell apart with a null dereference somewhere, but can't fix every bug at the same time. Yeah, it's a null dereference. In user space, that things just fall apart when we try to tear down the Quake process. I don't know why, but that's a different issue. So what did we have here? Those changes in system server, right? I can probably leave those alone, actually, because what is the value of this? Like, once they want to run, most of the time they just sleep, right? They sleep for a whole second, and then when they want to run, you might as well let them just get their paint finished and go back to sleep again. Otherwise, you're just desyncing, or not desyncing, but yeah, like you're delaying that visual update a little bit, just for the sake of letting someone else run first. I think we can probably keep them at normal for now. So we're adding a syscall set thread boost. You can only call it on your own thread, or if you're a super user, I mean, you can call it on threads in other processes as long as you own that process, or if you are the super user. It doesn't find dead threads or dying threads, and I think that's pretty good. All right. And then the thread from TID, right? So the effective priority of a thread is now the base priority plus the boost priority. Maybe we should call it the boost priority. Priority boost. Priority boost is okay. So effective priority is base plus boost plus extra. Cool. And here we just ignore any errors that happen. Let's be nice and at least log if something goes wrong. So we'll do this here, set thread boost. Okay. Quite nice. We'll write this slightly differently. We'll write it like this instead. Client. Active client, we'll say. Oh, wait, hold on. If we're switching between two windows in the same process, we don't need to deboost and boost because they're the same. So instead, we can do something like this. If let's say auto previous client is the previously wait, does this return early anywhere? It doesn't. Okay. So the previous client is going to be a WS client connection, previous client. Null footer. Previously active client. Okay. And then here we'll say previously active client is previously active window client. And here we'll say active client, same active window client. Okay. Then when we're done, we'll say if previously active client. And previously active client is not the active client. Then we deboost the previous one. If active client and previously active client is not. I guess we can check that once, actually. Boost. All right. That's a bit nicer because then we don't bother like deboosting and reboosting same thread if two windows in the same process. If we just switch between them. Otherwise, we would be doing that, which would be a bit silly. So let's just try something out. So now browser is running with effective 40. I wanted something that has multiple windows. So I guess we'll bring this guy up and we'll open up the properties window. And we'll see that file manager. Wait, oh, that's interesting. File manager, yeah, file manager icon changed because we opened a window with an icon, I guess. That's really goofy. And now everything is kind of sluggish for some reason. Why is that? Or is it? I can't even tell. Maybe it was just my mouse. I think it was just my mouse being weird. Because it stopped. I'm not sure. This is the kind of thing that would make you paranoid. Because I do have a mouse with a crappy battery. But that icon thing was curious. So like now, file manager has no icon. But probably we have some issue with the icon setting. Yeah. So I guess when we're opening a new window and setting an icon, that we replace the application icon. I never noticed that before. So we got a bug to fix there, but this was not about that today. So this was about the priorities, and good golly, I think we have succeeded in implementing a pretty neat system here and using it for something pretty neat. So I'm happy. Let's run the neon cat. So now terminal runs with a slightly higher priority, but that priority is not transferred to whatever's running in the terminal, and I think that's okay. It's probably something that we should figure out ways of doing, but I'm not exactly sure how we would do that. We can figure out something, but not right now. So let's run the fire demo instead. Look at it go. Okay, so I'm going to stop clicking around here and say I think this is going to be the end of today's video. So if you made it this far, then thank you for watching and for hanging out with me while I build a new scheduler, basically. Although we managed to reuse most of the existing scheduler, but this new algorithm is clearly pretty cool, I think. And I'm looking forward to building interesting optimizations using this. So I hope you saw something interesting here, and I hope your projects are going well as well. And of course, I hope your holiday is going well if you're on holiday. So thank you again for watching. And of course, I should mention more often that if you're interested in supporting my work, then I am on Patreon and GitHub sponsors, and there's also a one-time donation option thing using PayPal. You can find all of those things in the description below. I'm also on Twitter, although I mostly just post links to videos like this. But in case you want to talk, then Twitter is sometimes good for that. But most of the time, you just find me on IRC. Anyways, thank you, everyone. I still have one more day before the year is over, so I don't have to talk about that yet. But thanks, everyone, for watching, and I will see you next time. Have a great day. Bye.